Hello everyone. Here's a video on effects of solubility. In other words, what happens to solutions when we dissolve things in them. Okay. So looking forward here, the first thing, of course, we know that ionic substances produce ions. So we would expect that when ions are dissolved in solution, if I start off with 1 mole of NaCl, I produce 2 ions that are dissolved collectively, don't I? Okay. So each ion becomes solvated by water molecules. In other words, solvated means surrounded by. I say hydrated. It doesn't really matter. Okay. Now, so keep in mind, one of these produces 2 moles of dissolved substances. Okay. Whereas molecules, if we take a look at molecules, that only produces a 1-to-1 ratio. So there's only 1 mole of dissolved substances when I dissolve molecules such as this one. This is glucose. Okay, and that's surrounded by water molecules as well, okay, or hydrated or solvated or whatever you want to call that, okay. So just keep in mind that when I dissolve ionic substances, I get a doubling, perhaps even tripling or quadrupling effect. For example, let me go back. What if I take CaCl2 and I dissolve that and I dissociate it? You end up getting 1, 2, for a total of 3 dissolved ions. So in this case, this has a better effect whenever I'm trying to affect a solution by dissolving things in it. Okay. Now, this leads to something called colligative properties. We don't talk about colligative properties anymore in AP chemistry, but this is an example. You could either throw salt on your driveway or calcium chloride. Okay. We know calcium chloride works better than sodium chloride on when you throw it on your driveway to melt the salt. And the question is why or how? The reason is when sodium chloride dissolves, you only get 2 moles of dissolved substances that affect or interrupt the freezing process on your driveway. When you throw calcium chloride on there, why is this better and more expensive, by the way? You get 3 moles of dissolved substances. So you have a third more interrupting power on the freezing process on your driveway. Okay, so why don't they use this more in cities because it's so expensive? Okay, so calcium chloride does do the job a little bit better because you end up with 3 moles of dissolved substance rather than just 2 to interrupt that freezing process. Okay, that's a quick way to say that. It's a little bit more complex, but that's a good way to start that, at least see that. Okay. So which of the following is not true regarding the formation of an aqueous glucose solution? You can check this out. Here's the answer. Oh, geez. I hate it when that happens. Here's the answer. Okay. I think there's another one of these, but the heat of solution. This is, I believe, MC delta T. Not too bad. You can just check this out. The answer is A. That should be a simple one for you guys. Okay. How much would the temperature of the solution? Again, now we're looking at solving. It looks like delta T here. The answer is B. Okay, pause when you need to. So structure and solubility, I think we've looked at this before. I'm not going to deal with this too much. You notice that this structure is very nonpolar. I should probably use black. It's very nonpolar, okay? Doesn't have any hydrogen bonding. It's a very balanced molecule. So this is nonpolar, this is nonpolar. Whereas if you take a look at this is polar because it's very difficult to dissect this some way. How do you dissect this, or bisect it, I should say, to get something that's balanced or symmetrical? So that's why this is polar. Okay, real quick on that. Now, pressure and solubility. Pressure has no effect on, and if it is, it's very slight when I'm dissolving liquids and solids in water. But gases have a huge effect. In other words, gases increase in solubility with increased pressure. This is how they make carbonated beverages. So what do you do with a gas is if I have a bunch of gas molecules, perhaps this is CO2, okay? This is water, and I'm trying to make soda, okay, or pop, or whatever we call it out here, okay? They push the CO2 into the water, causing more of it to dissolve, okay? So increased pressure leads to increase in solubility for gases alone. not for solids and liquids dissolving in water. Only gases dissolving in water does that effect increase, okay, with increasing pressure. Temperature and solubility. In general, you increase the temperature, you increase the solubility, okay? Now, there are a couple outliers here. Like I said, I try to avoid always and never, but there are a couple outliers where this doesn't happen. But typically, you increase the temperature, you can dissolve more of it, okay? And you would need to see a graph or some data in order to be pretty sure of that. Um, Gas particles have predictable solubilities. As temperature increases, gas solubility decreases. So temperature in gas solubility is the opposite of pressure in gas solubility. Typically, as I increase temperature, gas solubility decreases. You get less gas dissolved. This an example of this is in the hot summers when you have like 10 days above 90 degrees. There tend to be a lot of fish that die or a lot of plants that die. I should say fish, not plants, because what happens is the gas solubility of oxygen goes down because the water in the ponds, at least stagnant ponds, this can happen. Um, the gas solubility of oxygen goes down because it's so hot. The water temperature rises, gas molecules of oxygen do not stay dissolved in the water, and the fish tend to suffocate. Okay, so this tends to happen. These are extreme cases, but it's something that definitely happens. You can see how warm pop is more fizzy than cold pop. Period. That is not debatable. Okay, sometimes you guys try to debate me on that one. Okay, vapor pressure of solutions. If I dissolve something in water, vapor pressure goes down. Let's take a look at this. So this is a pure substance, okay? This is just water here, okay? And it's got a certain vapor pressure. Let's say this is capped, okay? Now taking a look at this. Now notice there's nothing at the top except for water molecules. So that's all that can evaporate is water molecules. We have vapor pressure of X. Now, you'll notice when I put in something that dissolves, it's not all water at the top. There is some dissolved ions. I guess there's pluses here for the ions. So they have to share the space at the top. So when this solution is capped, I don't get as much evaporation. So therefore, when I dissolve things in water, the vapor pressure of the solution is lower when things are dissolved. Vapor pressures of solutions are lower than the vapor pressure of the pure liquid alone. Okay? I think that's all I have for there. And that's it, guys. So I'll cap this one off. If you guys need any help, go ahead and email me.